Welcome to the next invited talk. I'm a substitute for the chairman, and I just learned that I have to do the job a second ago, but it's a pleasure because I have to announce Klaus Beckerlich, that I know for quite a while as a very tedious and innovative mathematician, and this is all I wanted to say. The rest is what he's going to demonstrate to us.
Yeah, thanks very much, Ralph. Thanks for the invitation to give a talk here. So what I would like to present is joint work with Charlie Elliott from the University of Warwick and Vanessa Stiles from University of Sussex. And the work we are concerned with is a sort of inverse conductivity problem, a special form of such an inverse conductivity problem. So I start by describing our situation. So we are looking at an elliptic PDE in divergence form minus divergence a of x gradient y equal to 0 in omega, together with the Neumann boundary condition, where the function g on the right hand side in the boundary condition is a given function, omega is a bounded domain. The function g satisfies this mean that its integral over g is 0, so that you can solve this problem. The necessary solvability condition is satisfied. And our main assumption in this situation is that the diffusion coefficient A is assumed to be piecewise constant. These constants are denoted by A1 up to AR. They are positive and given, but what we don't know is the set EI, where these constants are attained. So we assume that these are unknowns in our problem, and what we would like to do is we would like to reconstruct the sets EI from given observations. So here these observations are denoted by y-ops throughout the talk, and they are assumed to belong to some Hilbert space. Typically one would assume that these are observations on the boundary, but one could also think of other situations. So I've kept it a little bit more general here, but the typical situation would probably be boundary observations. So that's somehow the task which we would like to attack, and so that's an inverse problem, and we know this is typically an ill-posed problem, so difficult to solve. So let me just say something about applications. Where do these kind of problems occur? So one can think of applications in geophysics, where the variable y would be the pressure of a fluid, and one would like to reconstruct from observations of the pressure on the boundary or on a part of the boundary a decomposition of a reservoir. Another application could be a problem in tomography, where one would look at y as a variable related to the electric potential, and one would like to reconstruct or to say something about the location of different tissue types in a part of a human body, for example. So these are kind of applications, and so there's some connection to this problem of free boundaries, because in the simplest setting which one can think of, so if this is our domain omega, a situation which people often look at is that the one set, say there is diffusion coefficient A1 in one part and A2 in the outer part, and this is somehow the region A1 where it's attained A2, A1, there is a boundary between these two, and we can try to look for this boundary and try to find this boundary, and then we have somehow solved our problem. So, and then the question occurs, how do you, if you try to solve it numerically or theoretically, how do you describe the boundary? And there are essentially two ways to do this. You can go for a parametric description and then try to come up, for example, with some numerical method in order to reconstruct the boundary. There is work by Hettlich and Rundle, Key and Sheen. And what has become very popular in the last decade is to use a level set approach. I've listed some names and papers. This is by no means a complete list. So there's a lot of work using the level set approach in order to attack this problem. I don't say much about the theory, but a good source is the book by Isakov on inverse problems for partial differential equations, where there are some chapters devoted to this kind of problem, especially to the situation here, where you have just two diffusivity constants. So to describe the problem or the approach in an informal way, I denote by M the set of all possible partitions of omega. So this is now informal. What you do is you can take an element E in M and associate with E the weak solution of our Neumann problem. So you have, in some sense, a mapping which assigns to an E the weak solution where the diffusion coefficient is given by A of x is AI when x is in the set EI. So this is the decomposition here. And then you can look at the mismatch between the solution and the observed data, and you can try to minimize this. Since we know that problem is ill-posed, typically in these kind of methods, one regularizes the problem, and for these types of problems, perimeter regularization is very popular. So one adds sigma is a positive term, positive constant. One adds these sums of these boundaries of the sets EI, and by this term you regularize the problem. It's called Tikhonov regularization, and you end up with a sort of an optimal control problem where it's an elliptic optimal control problem because the state variable, if you like, is a solution of an elliptic problem. So that's why we speak here about an elliptic optimal control problem, and it's controlled by this variable E here. So that's the control variable. The trouble is that it's, I will be a bit more precise about this, it's a non-convex problem, so that makes the minimization rather difficult. So now this is in some sense informal, and what we would also like to do is we would like to work with functions rather than with sets, just as in your talk this morning. So one can go to this setting, which is more mathematical. We can look at the set X, which contains all L1 functions, which are vector valued, and the dimension of the space R relates to the number of different diffusion constants which you can have. The components of U are non-negative, and they sum up to 1. And then you can associate with a partition of omega just the function U, the vector valued function U, which contains in every component an indicator function. So that is a special element in X. There are other elements which don't have this form, but the partitions can be identified with these special elements in X. And so you need to understand then partition in a slightly generalized sense. So for example, if you take EI and EJ, then the measure of the intersection is 0. So in this sense, they are disjoint. And now you take as diffusion coefficient A of U just this sum. It's a linear function in U, AI UI, and this is bounded from below and above. A min is the minimal of these constants, A1 up to ER, and A max the maximal. So if you happen to have such an element here, then if you restrict it to E1, for example, put it in here, then you get A1. So you get back the definition of the diffusion coefficient, which I've done on the previous slide. And then you can define a mapping which assigns to an element U belonging to this set the weak solution of our Neumann problem. So this is this weak formulation of the Neumann problem which appeared at the beginning. And since you solve a Neumann problem, you've got one free constant. You need to fix one constant, and we fix it by this prescription. So we say that the scalar product of y with the function identical equal to 1 is the same as for the observation. So that's our choice, and you will see in a few minutes why this is a reasonable choice. So now we've somehow said how, so the set X is in some sense our control set, and we said how it relates to the state, that's the y, and now we can define the objective functional just as before, but we express everything in terms of U now rather than in these partitions. And so the objective functional has two parts. The fidelity part, this is this term, which just measures as before the mismatch between the observed data and the solution of our problem. And the second part is the regularization part, which was this perimeter regularization. So to make sense of this, we now have to assume that U belongs to this space BV on omega, where taking only as values the unit vectors E1 up to ER. So this means every component is a BV function which only takes the values 0 or 1. And in particular, then you can talk about this quantity here. That's the total variation of the derivative of each component. And since ui only takes values 0 and 1, you just get the perimeter of the set where u jumps. So this is an expression then for this perimeter regularization. And now you can look for minima of this problem. And there's still one major problem, is that this constraint that u of x only takes these finite many values, that's not a convex constraint. So that makes the minimization a bit unpleasant. And the usual way to deal with this is that one relaxes the problem. And this is the next step. And we use a phase field relaxation here. So we introduce a small parameter, epsilon, and the functional now looks as before. So the fidelity term is unchanged, and the regularization term now contains this epsilon here. And where we evaluated u is in k, this is now the set of all h1 functions, and the other conditions are as before. ui, components all non-negative, and they sum up to 1. And this regularization part is now of Cahn-Hilliard type, the usual sort of functional which you have maybe seen before. So it contains two parts, this epsilon over 2, the norm of du squared, plus another penalization, 1 over 2 epsilon, 1 minus the Euclidean norm of u squared. And now it's convenient to write it in terms of the components of the vector u. And if you do this for the first part, it looks like this. You just sum up the gradients of the components. And for the second part, you rewrite the 1 here in terms of the sum of the components. So this is what you get. And this second part now, what does it do? If you take epsilon very small, it will, at least in the minimization, it will force the variable ui to go to the values 0 and 1. It just wants to be close to these two values, and in between then it will have a transition layer. So the typical behavior of these phase field type approximations, the gradient here makes sure that the transition is reasonably smooth. Because of these constraints, greater or equal to 0, and ui also has to be less or equal to 1, we talk about a double obstacle phase field approximation. And what you typically see is that this transition layer is confined to width of proportional to epsilon, but really confined. It's strict. Yeah. So this is what we use. And now, of course, the question is, how does it relate to the original problem? And so we want to say something about the convergence as epsilon goes to 0. And the typical type of convergence which you use here is the gamma convergence. So that's the next theorem. So I'm only talking about the regularization part here. So we have the result that these regularized functionals with the phase field approximation converge to the regularized part, which was the total variation, the sum of the total variations. And so we were not able to somehow find a direct reference in the literature, but all the ingredients which are needed are there. So you just need to somehow combine them in such a way that it applies to our situation. But really there are not really new ideas required to do this. But still I would like to say a little bit about the things you have to do. The first part in this gamma consists of two parts. There is a lim-inf part and a lim-sub part. The lim-inf part means you need to show that for every sequence u epsilon k converging to u in L1, this lim-inf condition holds. And the idea to do this is to go back to this representation of the phase field approximation, which has a sum over these scalar parts. So this ui is a component, so you sum up in some sense a Ginzburg-Landau approximation or Cahn-Hilliard approximation for scalar variables, and there are classical results by Modica and Mortola and Modica which you can use here together with the observation that the sum of lim-inf is less or equal to the lim-inf of the sum. So this part is fairly straightforward once you have these results available. And there's the second part, the lim-sub part, which is a bit more tricky. And what you have to do in this case is you need to show that for every u in BV, so I should say here intersected with the set X, there exists a sequence U epsilon K converging to U in L1 so that this Lim sub inequality is valid. And there is a very nice paper by Baldo from 1990 who covered this vector valued case. So this is a problem for a vector valued phase field variable. So he dealt with this, and one can use his techniques and adapt them to our situation. So an important first step is when you start from such a U, this induces in some sense a partition, and you approximate this given partition by a sequence of beta partitions, polygonal partitions. Then you introduce the distance function to these sets D, the boundaries of EI. These are now, the EIs are now polygonal. And then you can define, once you have this, such an element of a sequence. So this needs to be defined everywhere, but the most interesting part is near the boundary, so near the intersection here. In some sense, somewhere around here. And there you can define it in this way, which I've done here. And so if you have experience with this kind of problems, then you expect somehow a scale distance function, and the sign which appears here, this is related to the special choice of potential which we've made. And then this kind of function turns up. You've got here the unit vector EI and here the unit vector EJ, which refer to these sets. So this is the kind of transition layer which you have, and then everything is a bit more complicated because there can also be three sets coming together and so on, but I'm not talking about this here. So once you've got this gamma convergence, the really nice thing about it is that you can relate minima. And this is the next step. So what kind of consequences do we have? First thing is that when we go back to our original functional, it had the fidelity term in it. But because the epsilon is only in the second part, it's enough to show that the fidelity term is a continuous perturbation to prove that J epsilon gamma converges to U, and that can be done. It's not very difficult. Second point is, if you have now a sequence of minimizers of J epsilon, then there exists a subsequence epsilon k going to 0, a limit U such that the subsequence converges to U in L1, and U is the minimum of J. So in this sense, we can now use these regularized functionals, these phase field approximations for our problem. We just work now with the J epsilons and try to find minima of this problem. The trouble is it's still very difficult. Finding global minima of a complicated functional is almost impossible. So what can we do? We can go for the necessary first order condition. So maybe we try to find functions or solutions which satisfy the necessary first order conditions. That means this is this condition here, the first derivative of J epsilon in direction V minus U is greater or equal to 0 for all V in K. So one has to be a little bit modest here. And if we want to go on from here, then the usual thing is to first of all calculate the derivative. This is what we've done here. So you take a direction W, and then you evaluate this derivative. This part here comes from the fidelity. So maybe I'll remind you, the fidelity term looked like this. S of U minus Y ops squared. So if you differentiate this in direction W, you get the first expression, this one, and then the second one comes from the Kahn-Hilliard approximation. That was quadratic in U, so this is what you get. And now the trouble is, or when you want to continue here, the trouble is that the W is inside the derivative of the solution operator. And so, for example, if you want to go to look for descent directions in order to decrease the energy, then this form is not very useful. Also, if you want to change the W, you always have to evaluate this expression, and it always amounts to solving an elliptic boundary value problem. That's not useful. So, and in controlled theory, one rewrites this expression using an adjoint problem. That's the next step. So the calculation of this derivative, and the joint problem looks as follows. This is this problem here. The joint variable is the P, and you solve this elliptic boundary value problem with this right-hand side. This comes from the previous slide. And you see, in order to solve this problem, you take eta equal to 1 in here. That's the necessary condition for solvability. And this with eta equal to 1, this should be 0. And this is just the condition which we've prescribed on the solution of the elliptic problem. So that's why we made this choice for fixing the constant. So we can solve this problem. And furthermore, this derivative of the solution operator in direction w solves this problem. That's not very difficult to see. So this turns up here, and the w turns up here on the right-hand side. And here we use that a is a linear function of u. Otherwise, this would be a bit more complicated. So now you can put everything together. So I've done this here, but maybe to see it, I go back to the previous slide. So here, first of all, in this term, we use this function as a test function. And so then here you put in s dashed of w in here as a test function. Then you get this expression from the dual problem. And then you put the p in here as a test function, and you end up here. And what you've gained by doing this is the w is now outside here, and it just appears in a linear way. And then you can you easily can calculate derivatives, and you can easily find descent directions. So that's the virtue of this adjoint calculus. So now critical points. I've already written them down in an abstract way. This was this condition over here. J epsilon dashed in direction v minus u is greater or equal to 0 for all v in the convex set. And now if we translate it using the formula for the derivative, then we get this condition here. So that's our critical point. And what it really is it's a system of for 3 variables. For the phase field variable u, this is here, it's vector valued phase field variable. Then the y appears in here. Y is the solution of the elliptic problem for the given u, and for the p. And p solves the adjoint problem. So it's a system where you have a variational inequality and 2 boundary value problems. And you try to find solutions of this system and hope that maybe they are at least a global minimum, at least a local minimum. Maybe a global minimum, but at least a local one. And how can we get this? The strategy is, one possible strategy is to go for a gradient flow. So we look at an L2 gradient flow for the functional j epsilon and hope that it converges as t goes to infinity, and the limit, if it exists, would be a candidate for a critical point. That's the strategy. And now it's written down for this diffuse interface approximation. If you try to go back to a sharp interface limit, unfortunately there's an error on this slide. You get something which we already seen today in Matteo Novaga's talk. There is an evolution law which is v is equal to sigma times the mean curvature, and this bracket here should be over here. So you get a jump across the interface, and what you have in this jump are the solutions of the boundary value problem and the joint problem, and they jump across, the gradients jump across the interface. And this also enters the evolution equation, so it's a non-linear or non-local evolution law for these curves or surfaces, and hopefully you let them evolve, and hopefully they evolve to some limit as t goes to infinity, and that would be a candidate for the boundary which we are looking for. So it's a rather complicated process, but that's what it is. So now we would like to do calculations with this, and so the next step would be to discretize the problem. And so we start with a regular triangulation of omega, so a subdivision of the given domain omega into, just think 2-dimensional, into triangles. And then we have the standard finite element space. You take continuous piecewise linear finite elements, and then we can also discretize the control set. These are vector valued functions, and every component belongs again to this space of continuous piecewise finite elements. All the components are non-negative, and again they sum up to 1. And now we approximate the solution operator, which assigns to every control a solution of the boundary value problem. We now do it in a finite element setting. So that's the discrete solution now here. I call this operator SH. H refers to the fineness of the triangulation, the maximal diameter of a triangle. And this is the discrete solution. And then you can define a discrete functional, J epsilon H, and it looks just the same as before. The only difference is that in the fidelity term, you now take the discrete solution, the finite element solution. Now you try to minimize this. And now we keep epsilon fixed, and now we look what happens when you let the mesh size tend to 0. Does it somehow converge to the original problem? And this is the case. So we've got two convergence results. So for fixed epsilon, we suppose that UH is a minimum of our functional J epsilon H. So for this discretized version. And then you can prove that every sequence UHK, so of minimizers, of absolute minimizers, has a subsequence which converges strongly and almost everywhere to a minimum of J epsilon. So in this sense, this is consistent, this approximation, but it doesn't really help us so much because in practice we are not going to be able to find absolute minimizers. That's very difficult. So but we also have a convergence result for the critical points. So suppose UH is a critical point of J epsilon H just in the same way defined as for the continuous case, then every sequence UHK has a subsequence that converges strongly and almost everywhere to a critical point of J epsilon. And that's a bit more realistic, that we can find such critical points. And this is now the next aim which we would like to address, that we try to find a scheme, numerical scheme. So now epsilon and H are fixed, and now we try to come up with a scheme which gives us a critical point, which converges, so the solutions of the scheme converge to a critical point. And the starting idea is to go back to this gradient flow. So this was our gradient flow idea to approximate critical points. And if you now replace this part here, this derivative, by our formula which we found, then you get this expression over here. So these two terms came from the formula for the directional derivative of J epsilon. And now we turn this into a scheme. So what we do is we replace the time derivative here by a difference quotient, and then all the other terms need to be evaluated at the time level. So that's what it looks like. The first term is the approximation of the time derivative, and here you see, maybe I can go back, there was v minus u, then there are the other terms, and now you have to make a choice. Where do you evaluate the variables? You can evaluate them at level n plus 1 or at level n, and you have something implicit or explicit, and this is the choice we made. And first question is, does this problem have a solution? So given here is the un, you start with something, some initial value, and you assume you are at level n, then you want to calculate un plus 1, and this can be done, and it can be shown that given un, you can solve. So here's the remark which justifies this. You can prove that un plus 1 exists uniquely as the solution of a strictly convex minimization problem. So it exists, and the UNH here is the solution for YNH is the solution for UNH, and PNH solves the dual problem. And now the question is, does this converge? And does it converge to a critical point? And this is possible. So we have the following result. We can prove that if the time step tau, there's a time step involved in this, satisfies a certain condition. This is something you would expect because there are some terms are taken explicitly, and so you expect a time step constraint, and you can write it down explicitly. If this condition is satisfied for tau n, then the energy decreases. So that's the first thing, and this is the most important thing, and also that you have this term over here. The constants which appear you can calculate them. There's maybe one difficulty about the constant c hat, which is some sort of Poincaré constant, which you only can calculate in special cases. But it might be enough to just have an upper bound for it. But in principle, all these terms can be evaluated at time level n. Then you have a constraint, and then you can guarantee the decrease of the energy up to the next time level. And this then helps us to, I don't talk about the proof here, I don't think that's very helpful. You can then prove that whenever you start, you can take an arbitrary initial value, then you can prove that there exists a constant gamma, so that these tau n are bounded from below. This constant gamma may depend on h, but here in this setting we have fixed h and we fixed epsilon. And then you can prove that the sequence of these iterates which you generate have a subsequence which converge to a critical point. So this is guaranteed to converge if you satisfy these time step constraints. And so this is in some sense the theoretical part. So we've gone through a number of approximation steps. In the first step, we have approximated this functional j by these relaxed functionals, and we've justified this by gamma convergence. In the second step, we have approximated the functional j epsilon by finite dimensional problems, and we have seen that at least it's possible to construct critical points by an iteration. And now, in the end, I would like to show you some tests. We've done tests on a square domain, omega, and we've just used one measurement. The function g is defined in this way here, and we have done tests with 2 different diffusion coefficients, a1 and a2, and with 3 different diffusion coefficients, a1, a2, a3, and the tests were set up in such a way that we took an exact partition, and then we calculated for this exact partition a discrete solution. This is denoted by yh tilde, and then we generated the observations by just perturbing this discrete solution via random noise. And then the question is, what does the algorithm do with these data? And this is what we got. This is on the left-hand side, you see the exact partition. So that was this ux exact, and this is what the algorithm gives us. So you see there is some smoothing in there. This is because of the phase field approximation. There's a gradient in the phase field approximation which smoothes. And here we used distributed measurements. So the space O, the observation space, was L2 of omega in this case. So this is maybe not very practical, but I mean, we are beginning to start to test these algorithms. The other parameters were chosen. Epsilon was 1/16 pi, and the regularization parameter sigma 10 to the minus 5, and there was no noise in this experiment. So the next test, this is now boundary measurements. Here again, this is the exact partition which we prescribed. Then this calculation here refers to the situation that you have no noise in here, and the second is a calculation with noise where delta was chosen to be a 0.005. So you see we get there, and this was, by the way, by choosing any initial data. So they were chosen randomly. So this worked pretty well. And here's an example for the 3 different values. Again, the upper one is the one which we prescribed, and the lower one is the result of the calculation. And this also works. But you see the smoothing again. So especially in the third example, you see that it tends out to smooth these sharp corners. But these look fine, but we also encountered situations where we ran into local minima, and then it doesn't look so nice. But if you start close, okay, it's how do you get close to these things? But if you start pretty close, then it converges. If you start somewhere randomly for more than 2, then it might become a bit more tricky. And with this, I'd like to stop, and thank you for your attention.
Questions? So I have two questions about this evolution equation you've been writing down. So did you derive this evolution equation for the sharp interface setting rigorously? And did
No.
you consider any conversions epsilon during the evolution equation?
No. This is just a formal argument. So this is purely formal. When I write down the energy for a sharp interface approach, this is what I would get. But there's no convergence analysis. No, I think that's very difficult.
For two phases, it would be possible. Or
If there is a chance, then I think for two phases, yeah.
Similar question. You show existence of critical points for epsilon positive, and you cannot pass to the limit in epsilon going to zero in the critical points and get some sort of critical point in the sense of Tonegawa for the Allen-Kahn energy.
Okay, I don't know how this is defined, but no, I haven't tried it. Maybe you can tell me how this is defined. So that would be the first problem. What is the notion of critical point for this for the limit functional? So.
Did you say anything about the uniqueness of the conductivity?
Well, there are only in special cases you have uniqueness. So, for example, in this case, uniqueness you only have in a certain class of shapes. So, for example, within circles you have uniqueness. Always, if you have only one measurement. So, if you have only one measurement, uniqueness is very difficult. If you have infinitely many measurements, or you know the complete Dirichlet to Neumann map, then uniqueness results are stronger. But
in your case, do you observe the non-uniqueness from one measurement?
In these cases, not. No. But if we take more complicated shapes, then I think we will observe this. And we've got the problem of running into local minima.
Any other question? Okay, I have one. So do you have to fix the number R, or can you search over R as well?
It would be. You mean that we can?
So in other words, you imagine you have R distinct values of A.
But without knowing the values, I think it.
Without knowing how many.
Oh no! I think the way we treat it at the moment, we couldn't do this. Yeah, there are approaches. There is a paper by Rondi and Sandoza who use methods from imaging. For example, the Mumford-Shah functional to subdivide to find these regions without prescribing any number of different diffusion coefficients. But the way we treat it, we in some sense have to fix the dimension of the vector field, and so we are stuck with this. Yeah.
Yeah. Then the other question, which you were going to answer, was if you don't know the diffusion coefficients.
Yeah, so there we could include this. Yeah, so that's possible. That's a possibility that we could do this as well. Would just be another term in the functional.
Okay, let's thank Klaus for a very nice talk.